Alright, so in this video we go over section 5.7, complex zeros and the fundamental theorem of algebra. Alright, so the objectives of this section is to use the conjugate pairs theorem, find a polynomial function given some specified zeros, and find complex zeros of a polynomial function. So what about the conjugate pairs theorem? Number one, so we are going to go back to a definition very similar to that of our very beginning of this chapter, in which we defined the look of a polynomial function. So in this case, a generic polynomial function looks like this: big polynomial, the leading term has tell us the degree, which is n, it cannot be a zero, and this is the constant term. And again, like we went over on the previous section, a complex number r, in this case we're going to extend the concept of the rational root theorem to complex zeros. Complex number r is a complex zero of the polynomial if we plug in the value of r in our polynomial here and our answer is 0. In other words, we have a zero remainder if we did the what's it called, synthetic division, if you will. Okay, fundamental theorem of algebra, what is that? So it states that every complex polynomial function of degree, there was a little typo here, that it should say of degree n has at least one complex zero. Okay, every complex polynomial is another theorem, so in which we say that we can factor a polynomial into n linear factors, and in this case not necessarily distinct, and that comes from the fact that some of the factors may have a multiplicity 2, multiplicity 3, they could be repeated, and you will see some examples about that soon. And it looks like this, and a sub n is a choice of n, or depending on the leading coefficient in lowest terms of the polynomial. Conjugate pairs theorem. So we're going to have a polynomial f of x whose coefficients are going to be real numbers. So if we are given that r equals a plus bi, whatever complex number is a complex zero of the function f, then its conjugate is also a zero. In other words, if you're given that one of the zeros is an imaginary number or a complex number, strictly the other, its counterpart, which is the conjugate, it's going to be a zero. For example, if r1 equals 3 plus 5i is a zero of the polynomial, well then that should be a freebie that r2 will be 3 minus 5i. On the other hand, if I have something like r1 equals 3 halves minus, I don't know, 7 thirds I to be one of the zeros, okay, then strictly r2 will be 3 halves plus 7 thirds of I. And a consequence of all these ideas right here is that a polynomial function of odd degree, okay, a polynomial of odd degree will have at least one real zero. For example, well, let's illustrate that idea. So for example, we have a polynomial of degree 3. Well, there could be two cases. Number one, all three zeros are real. That's one case. But the other case is, for example, if one of those zeros is complex, well, keep in mind that the complex always travel by pairs. Whatever complex zero and its conjugate, so it's going to be 2 complex, and the remaining, which is 1, will be real. Degree 5, for example. Maybe we are going to have the scenario in which the 5 are real. If we know that only one is complex, well, we know its counterpart or its conjugate, in this case 2 complex, and the remaining 3 are real. And the third case scenario for a 5th degree polynomial, okay, because we're looking at odd degrees, well, maybe we can have 4 of them complex and 1 real. In either case, degree 5, degree 3, there's at all case scenarios has at least 1 real 0. Okay, let's look at some examples. So if find the remaining zeros of f of x whose coefficients are real numbers, given that the degree is 4, okay, and the given zeros are these 2. So these 2 zeros are given. One of them is 2 minus I, and the other 0 is negative I. So in this case, we are going to have how many zeros? Well, because the degree is 4, we are going to be having 4 zeros. So R1, R2, R3, and R4. Okay, we're given 2 minus 1 is one of the zeros. I mean, not 2 minus 1, 2 minus I. Okay, by the conjugate pairs theorem, strictly its conjugate has to be another 0, 2 plus I. Then we're given the negative I is one of the zeros. Then by the same idea, positive I is the other 0. So here is all 4 zeros of the polynomial. Alright, we're going to find a polynomial function with specified zeros. So this is going to lead us to a theorem that tells us that every polynomial function with real coefficients can be uniquely factored over the real numbers into a product of either linear factors and or irreducible quadratic factors. Okay, how is that going to look like? How are we going to use all this and all the theorems that we mentioned earlier? So let's do an example. Okay, form a polynomial f of x with real coefficients having a degree 5 and zeros, which is one of them is 1 of multiplicity 3 and the other one is 1 plus I. Wait a minute. They are giving us only 4 in the information here in the text. However, keep in mind that 1 plus I will be the 1 minus I will be the other, the 5th zero. Okay, so answers may vary depending on the choice of the leading coefficient, and for the sake of simplicity, let's use a equals 1. Okay, for simplicity, use a equals 1. Okay. All right. So that means we have R1, which is multiplicity 3. So in this case, R1, which is 1 of multiplicity 3. Then they are giving us another 0, R2, which is 1 plus I. And consequently, we're going to have R3, which is 1 minus I. Okay, 1 minus I. So, multiplicity 3 plus 2 more zeros, that's going to give us the overall degree of 5. All right, so we're going to use the theorem, the theorem one of the theorems we stated earlier, in which some polynomial f of x can be written in as a product of linear factors, in which a What did we say about this one? A sub n, and then the product of linear factors. But in this case, a sub n, we already say that for simplicity, use 1. But I'm going to write x minus r1. But what did we say about r1, which is multiplicity 3, and then x minus r2 times x minus r3. Okay, so I'm going to write those zeros where they correspond, and for a sub n, I'm going to replace with a 1. In other words, I'm not going to write anything. So r minus 1, okay, minus r1, which is 1, quantity cubed, times x minus, careful with what we're going to write here. This might look familiar from the previous video, the review video. That's going to be 1 plus I times x minus 1 minus I. All right. So in this case, what are we going to do? Well, I'm going to do the following. I'm going to distribute this negative sign over here and there. Okay. So f of x will, I'm going to do two things here. Number one, because if you have seen this binomial cubed in the past, well, then you can do it. However, that's something we're going to do at the very end of the semester. So what I'm going to do, I'm going to break this up as it is not r, this is supposed to be x. X minus 1 quantity squared times x minus 1, because x minus 1 squared times x minus 1 is going to give us x minus 1 cubed. And then when I distribute this, I'm going to get the following: x minus 1 minus I times x minus 1 negative times a negative positive I plus I, x minus 1 plus I. All right? Now, there's two things I'm going to do here. Number one, I'm going to expand this binomial. So remember the review we did to expand binomials? So you don't do a lot of FOILings here. So the next move here will be f of x equals, so x squared minus 2x plus 1 times x minus 1. Now, what about the product of these two trinomials? Remember what we did on the previous video, the review video. If you haven't watched it, I would recommend you watch that video first, and then we move on and then come back and watch that video. So what I'm going to do, I'm going to use the trick I use. Well, it's not necessarily a trick. It's just algebra of grouping here, grouping terms. Nothing illegal, nothing weird. So I'm going to group these guys. That's going to be my A, and that's going to be my B. Maybe I should have used, so A minus B times A plus B. That's going to give me something of the form of a difference of squares. So let me highlight with So I'm going to get the following. I'm going to get something of the form of A squared minus B squared. So x minus 1 squared minus I squared. All right? So what's our next move? The next move is I'm going to expand this binomial the same way I did it here. In fact, it's nothing different than this. I'm just going to copy. And then I'm going to FOIL this. So for this one, there will be no way around. We will have to FOIL this. There will be no trick to shorten the calculations, the calculations here. So what I'm going to do is I'm going to f of x equals, so x times x, and that's going to give me x times x, that's x cubed. And then x times -1, negative x squared. And then negative 2x times negative x, that's negative 2x squared. And then negative 2x times -1, that's positive 2x. And then 1 times x, that's a plus x. And positive times a -1, that's a -1. All right. Inside of the brackets here, I'm going to use parentheses instead of brackets. I don't need brackets anymore because I'm undoing this parentheses here. So this is going to be x squared minus 2x plus 1. And then minus, what is I squared? Remember what is I squared? Keep in mind that I squared equals -1. All right, don't forget that one. That's from chapter 1. And that's going to be minus -1. Careful, we're going to use the smile rule, right? Turn that into positive. And here I'm going to simplify like terms. 2 bars for squares, 1 bar for linears. Oops, only 1 bar, not 2. All right. So let's see. So this will, I'm going to simplify this one. So that's going to be x cubed minus 3x squared plus 3x minus 1. And this one times x plus x minus 2x squared. I mean x squared minus 2x. And then that's 1. Negative times a negative is positive. It's plus 1. So 1 plus 1 is 2. So we're almost-ish there. So now what we need to do is FOIL this one. Again, there's no trick for this, but at least we save some work here using the difference of squares backwards, including using this little trick of grouping terms to make it work like that. So I'm gonna go at a little bit slower pace here. So x cubed times x squared, that's gonna give me x to the 5th. X cubed times x cubed times negative 2x, that's going to give me negative 2x to the 4th. X cubed times 2, that's 2x cubed. And then I'm going to go with the second term. Negative 3x squared times x squared, that's negative 3 times x to the 4th. And then I'm going to multiply by negative 2x. Negative times a negative is positive. 3x squared times 2x, that's a 6x cubed. And then negative times a positive is negative 6x squared. Multiplying this 3x squared with this 2. Okay, so far so good here. All right, and then I'm going to go with the 3x. So 3x times x squared, that's going to give me 3x cubed. 3x times negative 2x, that's 6x squared. And 3x times 2, it's plus 6x. And I'm running out of space here. Hopefully not. Hope I don't run out of space. This -1, I'm going to multiply with the 3 terms. Essentially, this -1 will change the sign of these 3 terms. So that's going to be negative x squared plus 2x and plus 2. Okay, so now it's time to combine like terms over here. So I'm going to use the same technique of bookkeeping, all terms. So I'm going to use a different color. So I'm going to have 4 bars for 4th powers, 3 bars for cubes, 2 bars for quadratics and 1 bar for linears. Okay, so quartics, cubics, quadratics, and linears, and everything else, the quintic and the constant term, are going to remain the same. All right. So what's next? Let's combine like terms this time, f of x, and we're done with this. So x to the fifth. And okay, what about the quartic terms? So negative 2 minus 3, that's a negative 5, x to the fourth power. Then what about the cubic term? So that's 2 plus 6, that's 8. 8 plus 3 is 11, x cubed. What about the quadratic term? So negative 6 and negative 6, I believe I did a silly mistake. Did I? I don't think I did it. Because I have 6x minus. Okay, I believe this one is supposed to be negative 6x squared. I did a silly mistake. So negative 6x minus 6x minus 6 negative 6x squared minus 6x squared, that's going to be negative 12 minus 1x squared, that's a negative 13x squared. So let's see, where did I get the mistake? So here I multiply this 3x times 2x, which is 6x squared, but I forgot to multiply this positive with this negative. So that's where the mistake came from. And finally, the linear 6x plus 2x, that's 8x. And then plus 2. So we are done with, minus 2. This should have been a minus 2 as well. Negative times a positive is negative. This is supposed to be a negative. Okay, so when you're doing a problem like this on the homework, on the exam, need to take your time, need to watch for those silly mistakes like I did, even though I have the work right here next to me in Scratch. When I was doing this, I made a silly mistake. And you don't want to do this when you're doing your homework or when you're taking a quiz or an exam, right? So that's an example. Okay. Let's do another example. And the next example is use the given 0 to find the remaining zeros of the function h of x equals 3x to the 4th power plus 5x cubed plus 25x squared plus 45x minus 18. And in this case, one of the zeros that we are given is 3i. Okay, but what do we know every time we're given at least one of the imaginary or complex zeros? So we're given, in this case, a complex zero. So we know that this function, 3x, okay, let me write it down. 3x to the 4th power plus 5x cubed plus 25x squared plus 45x minus 18 will be factored into the product of x minus r1, x minus r2. Because it's degree 4, we're going to have 4 factors here. All right? X minus r3, x minus r4. All right? So here, in this case, we are given one of the zeros. One of the zeros is 3i. By the conjugate pairs theorem, there exists another zero, which in this case will be negative 3i, which is its conjugate. Okay, is its conjugate, and that one will be here. The other two will figure it out. Don't worry too much about it. First, let's work with the information that we already have. Let's see how can we use that information. So we're going to have x minus r1, which is 3i, times x minus negative 3i, which is the other 0, times x minus r3, x minus r4. So in this case, we're going to have x minus 3i times x plus 3i times x minus r3 times x minus r4. All right, if you identify this form, remember what we did on the previous video. Let me see if I have those notes here. I believe I do. Let me check if I have that example in particular. Well, I had something like this on the previous video, but I had it with a 6. Rather than doing the foiling, x squared, 6 squared, but instead of having a minus, a difference of squares, we're going to have a sum of squares. So let's use that same idea. All right, so in this case, we're going to have x squared plus 9 times x minus r3, x minus r4. All right, now let's see. This is the same as here. All right, 3x to the 4 plus 5x cubed plus 25x squared plus 45x minus 18. Now, how are we going to find those two remaining zeros? All right, so I'm going to divide both sides by the quantity x squared plus 9. And the remaining zeros, x minus r3 times x minus r4, will come from, guess what? Polynomial long division between these two. 3x to the 4th power plus 5x cubed plus 25x squared plus 45x minus 18 and x squared plus 9. Divide by that. So we're gonna do a polynomial long division using those two polynomials. Now the reason why, if you think about, well, can we use synthetic division for this case? The answer is no. And the reason why is because the denominator, it's a quadratic binomial, not a linear binomial. If we had like x plus 9 only, well, then we're good to go, and we do synthetic division, put a minus 9 and just write down the coefficients. But this is not the case, unfortunately, so we will have to deal with polynomial long division, which I am about to set up. Okay, let me use maybe a different color here. How about I use maybe, do I have green? I don't think I have green. Okay, I have this green right here. Okay, so I'm going to write 3x to the 4th power plus 5x cubed plus 25x squared plus 45x minus 18. And I'm going to divide that by, whoops, this one is dying on me. Okay, I better get another one. Let me get another one real quick. All right, I got it. There you go, new. So in this case, I'm going to divide by x squared. Remember those placeholders, 0x plus 9. And we do that in order to have everything organized nice and neat by columns of powers. All right, so let's see again. Remember, we divide the leading 3x to the 4, divide that by x squared, we get 3x squared. And then when I multiply 3x squared times x squared, we get 3x to the 4, but we change the sign. All right, and then let's do the division. 3 times 0 is 0, x cubed. 3x squared times positive, that's negative 27x squared. All right, again, because product of two positives is positive, we change that to negative, and that's supposed to be a 2. All right, okay, let me write it more nicely. Okay, squared. Okay, so I'm going to cancel this out, cancel these guys, and I'm going to add 5 plus 0, which is 5, 5x cubed, and then 25 minus 27, that's a negative 2x squared. And then drop the next term, which is 45x. Now, I'm going to focus on this leading 5x cubed, divide that by x squared, we get 5x. All right. So 5x times x squared, we get 5x cubed. But again, remember, we changed the sign of what we obtained. 5x times 0x, that's 0x. 5x times 9, that's 45x. 5 times positive times a positive is positive, change that to negative. So in this case, these guys go away, these two go away. Well, so I'm going to remain with negative 2x squared, right? Negative 2x squared, and then I'm gonna add this placeholder, not the one in the leading, only this one. I need a placeholder 0x, and I'm gonna drop the constant term, which is negative 18. And again, I'm gonna divide negative 2x squared by x squared. I'm gonna get a negative 2. And I multiply negative 2 times x squared, I'm going to get 2x squared. But a negative times a positive is negative, make it positive. Negative 2 times 0, that's a 0x. And then negative 2 times 9, that's negative 18. Change it to positive 18. Okay, so boom, boom. 0 plus 0 is 0. Negative 18 plus 18 is 0. So 0 remainder. What are we going to obtain? The quotient is this guy. All right. So now h of x, let's go back to the original problem. H of x, well, I'm not going to write this huge polynomial. I'm going to write what I have in terms of factor. All right. So h of x equals, okay, so in this case, I'm going to go back to its factored form, x plus 3i times x minus 3i times the polynomial I got here from dividing these two polynomials, which is 3x squared plus 5x minus 2. Now, in this case, we don't need to do any synthetic division or anything weird because, well, in this case, we didn't do any p over q. So what we could do with this trinomial is factor. So in this case, the leading coefficient is different than 1. I'm going to use this diamond method to factor these guys. So I'm going to use a different color here. 3x squared plus 5x minus 2. So 3 times negative 2, negative 6, and 5. Factors of negative 6 that add up to 5, negative 1 and 6. 6 minus 1 is positive 5. 6 times negative 1 is negative 6. All right. So I'm going to split this into negative x, 6x, minus 2, 3x squared. So I'm going to use factor by grouping over here to factor this trinomial. GCF on the first group is x. We're left with 3x minus 1. GCF on the second group is 3. No, not 3, actually 2. I'm left with 3x minus 1. And the new GCF will be 3x minus 1 that multiplies x plus 2. Okay. So now this will become x plus 3i, x minus 3i, and the two remaining zeros are x plus 2, or this order doesn't matter again, 3x minus 1. Alright, so let's see. From the first factor, well, these two zeros were already a freebie, so the first zero is x equals negative 3i. The second zero is x equals 3i. And then the third zero is x equals negative 2. And the fourth zero is x equals 1/3. So those are the four zeros, right? So let's do one more example. And call it a day for this topic. All right, find the complex zeros of the polynomial f of x equals x to the 4 plus 2x cubed plus 22x squared plus 50x minus 75. All right, so in this case, we are not given any kind of information. So for example, on the previous example, they gave us a hand actually. By giving us one of the complex zeros, we get that the second zero is the conjugate. Okay, it's the conjugate, so we need to use that information to get the other zeros. All right. Now, in this case, we don't have anything. So in this case, we are going to use a rational root theorem in this case. P and the leading coefficient 1, which is Q. So let's list all the potential zeros, P over Q. So P is going to be all the possible factors of 75, which by the way, it's going to be quite a bit. Okay, so plus or minus 1, plus or minus 3, plus or minus 5, plus or minus 15, plus or minus 25, plus or minus 75. The good thing is this one for the denominator is only plus minus 1. All right, so dividing every single number here by 1, well, it's only those numbers in the numerator of P of the ratio P over Q. So plus minus 1, plus minus 3, plus minus 5, plus minus 15, plus minus 25, and plus minus 75. So I'm going to have 3 and 3, that's 6 times 2, total of 12 potential zeros here. And what are we going to do? I'm going to start by, I'm going to test, I'm going to start with negative 1. Negative 1, so I'm going to write negative 1. The leading term, the coefficients of the polynomial, notice all powers are there, so I won't need to have any place holding zeros. So 1, 2, 22, 50, negative 75. And then, so let's proceed to do this synthetic division. Well, drop, multiply, and add. So negative 1, and then 2 minus 1, that's 1. 1 times negative 1 is negative 1. 22 minus 1, that's 21. 21 times negative 1, that's negative 21. And then 50 minus 21, I get 29. But 29 times negative 1 is negative 29. Combine these two numbers, negative 75 minus 29, that's a negative 104. So in this case, what did we obtain? Our remainder is not 0, so x equals negative 1 is not a 0. And consequently, x plus 1 is not a factor of f of x. Same reasoning as in the previous section. Alright, so what's next? So the next thing is to test another 0. So I'm going to test positive 1. So I already tested negative 1. I'm going to test positive 1. So 1, and then I'm going to write the coefficients. So this will be 1, 2, 22, 50, negative 75. Okay, so I'm going to drop the first one, the first coefficient, multiply 1 times 1, which is 1, added with this 2. 2 plus 1 is 3. 3 multiplied with 1 to get 3. 22 plus 3, that's 25. 25 times 1, that's 25. Plus 50, that's 75. 75 times 1 is 75. 75 minus 75, nice. This is 0. So we didn't have to go through too many zeros. So in this case, because just testing the second zero gave us the first zero. So x equals 1 is a 0. And consequently, x minus 1 is a factor of f of x. Now, I'm going to use all this information to show you all about the depressed polynomial. So keep something in mind here. One thing to keep in mind is this was the constant term, linear, quadratic, cubic, quartic. Now this is remainder, which we don't care, constant, linear, quadratic, and cubic. So far we are going to have f of x factor as well. I'm not going to write the original polynomial, it's huge. So I'm going to have what we have here, that one of the factors is x minus 1, and the remaining will be x cubed plus 3x squared plus 25x plus 75. X cubed plus 3x squared plus 25x plus 75. All right, so in this case, well, do you want to keep testing the rest of the zeros? Well, in this case, it may not be practical, because if you look at this polynomial can be factored by grouping. I know on the previous section at least I did one in which I repeatedly was using the zero testing just for the sake of practicing this synthetic division and to make connections with this and the rational root theorem. But by now that you have some practice with this, well, in this case, just take advantage of whatever you spot right away, which in this case is this factor by grouping. So f of x will be x minus 1, and x minus 1, and what is this going to be? Oh, that's going to be the GCF, or actually I'm going to use brackets because I'm going to factor the GCF, which is x squared times x plus 3, factor the 25, x plus 3. So the GCF is x minus 1, x plus 3 times x squared plus 25. How do we factor this x squared minus x squared plus 25? Remember that factors over the imaginary numbers. X minus 1, x plus 3, x minus 5i, x plus 5i. Final answer. I mean, this is the polynomial in factor form. Now they're asking us for all the zeros. So in this case, one of the zeros is x equals 1. The other zero is x equals negative 3. The other zero, x equals 5i. And x equals negative 5i. All right, so those are the 4 zeros. So there's another example I would like to cover, and what to do when you get one of these really crazy problems. I already set it up for you. So suppose you have this polynomial x to the 4 power plus 3x cubed minus 19x squared plus 27x minus 252. All right, so in this case, if you do the p over q, you are going to get all these many potential zeros. Just doing this is going to take forever. All right, now on top of that, you would have to test every single one of them, and trust me, when I was looking at an example like this, it wasn't pretty. I had to try synthetic division at least 6 or 7 times. I'll show you what I mean by that. Okay, so for example, I would have to test -1 and then 1. I had to test -2 and then +2, etc. So when you get something this crazy with like really big numbers here that gives rise to this many, in this case it's a potentially 36 if you count them. Let's count them again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 12, 13, 14, 15, 16, 17, 18. 18 times 2, 36 potential zeros. But ultimately we are going to end up with 4 of them. So this is what I'm going to do. So for something like that, let's see. So first of all, we're going to go to the y function and type the polynomial. Then from there, hit the graph. And it's going to graph it for you. In some cases, unfortunately, not every single case, you will be able to see the exact root crosses at exact lines. That is, the zeros are perfect integers. In some other cases, you will see the intersects going in like the middle of a line. You know, in that case, that means the 0 will be a rational number, a fraction, which is not going to be really easy to guess. So in this case, I can guess that +4 and -7 are the potential are 2 of the actual zeros. So now that I know that -4 and the +4 is one of the zeros, if we look at all of this, it would have taken me 1, 2, 3, 4, 5, 6, and then -4. That's the 7th test until it wouldn't have been until the 8th trial, the 8th synthetic division, before I get one of the actual zeros, and then I would have gone through all of this to get the +7, the plot to test +7 and the -7. So in this case, let's see. We know for sure. Okay, so from the calculator, I got that 4 is a 0. So I'm gonna test 4. So 4, and then I'm going to write the coefficients: 1, 3, -19, 27, -252. So I'm going to drop the first term, the first number, multiply, and add 4 plus 3. That's 7. 7 times 4. That's going to be 28. 28 minus 19. Let me use the calculator. 28 minus 19. So that's a 9. 9 times 4. That's a 36. 36 plus 27. I get 63. And then 63 times 4. I get 252. Which in this case is 0, which is nice, which is what we would expect it. So there's no way to get one of these zeros. If you get that, in this case we got that 4 is one of the zeros, then you must have a zero remainder here. Otherwise, double check your calculations, or maybe double check what you typed on the calculator. So again, let's go with let's write down this. Where's my marker? Let me use something, another color. Okay, constant, linear, squared, cubic, and quartic. Remainder, constant, linear, squared, cubic. So our given f of x is, in this case, well, x equals 4 is a 0. And consequently, x minus 4 is a factor of f of x. Okay, so f of x is going to be x minus 4 times x cubed plus 7x, x cubed plus 7x plus 9x plus 63. Now, you don't want to do the rest by testing the rest. Well, for sure we know that -7, we already did it in the graphing calculator, but come on. In this case, it's just way easier to do this by grouping. So x minus 4 times brackets x, well, this is supposed to be squared, by the way, x squared, x plus 7, factor out the 9, x plus 7, and the GCF is x plus 7 times x squared plus 9, but don't forget the other factor. So from here we get that x minus 4 times x plus 7, and how do we factor x plus 9? That's x plus 3i, x minus 3i. And the zeros are going to be x equals 4, x equals to -7, x equals to -3i, x equals 3i. All right, so that's how we deal with a problem when it's that crazy, when you don't want to do too many, or if, for example, if you are doing it the usual way. I mean, if you are a huge fan of synthetic division, you want to do a few, well, maybe after the third one or the fourth one, you might want to look at the graphing calculator and see, so you don't have to do all of that. Because what if you run into a situation in which, well, in this case, the first one, right, we got that 4 was a 0, so well, it didn't take too many synthetic divisions. But what if the first 0 is a 12? Think about it. Do you want to do 23, or no, not 23, 20, let's see, 1, 2, 3, 4, 5, 6, 7 times 2, 14, 15 synthetic divisions? Maybe that's a little bit overwhelming. So you may not want to go that many divisions. Use your graphing calculator. Alright, so I think this is a good place to quit. I'll see you on the next video.